All right, guys, this is going to be the non-calculator part of the review, the answer key. And we'll just get right into the first couple of questions, which is graphing. So plot two nice points and the asymptote and fill in the information for each function. So to begin with, I like to think of the parent function. The parent function here is just y equals 3 to the x. Sometimes we call these the original points. Like, what are the two nice points originally? So when you plug in 0 for x, you get 1. When you plug in 1 for x, you get 3. And exponential equations or exponential functions have a horizontal asymptote at y equals 0. The 2 that's in front of the function is multiplying every y value by 2. You have to do stretching and reflecting first. So this is going to become 0, 2, and 1, 6, and this will still be y equals 0. And then after you do that, then you take care of the translations. So this is left 4 and down 1. So I'm going to take all of these points and go left 4 is what that should say, and down 1. So I start with the horizontal asymptote. The horizontal asymptote is going to go down 1. The left 4 doesn't really show up. So I start there. And then the point 0, 2 is going to go left 1, 2, 3, 4, and down 1. And the point that's at 1, 6 is going to go left 1, 2, 3, 4, and down 1. And then I'll just sketch this curve in, and that's my graph. Okay, now everything else, I'm either going to use the graph or maybe a little bit of algebra. So the asymptote equation is y equals negative 1. Make sure you write the equation. It's important to know if it's y equals or x equals. The domain is all real numbers for every exponential. The range is, in this case, the asymptote is negative 1. Then the graph opens up to infinity. I'm going to do the y-intercept first because it takes less work than the x-intercept. So for the y-intercept, I can't get it just off of my graph. So remember, for any function, the y-intercept is to find f of 0. And we're just going to do the math. So 2 times 3 to the 0 plus 4 minus 1. All right, so that's 2 times 3 to the 4th is 81. If you don't know that one, you know 3 to the 3rd, hopefully, is 27. Multiply that by 3. 2 times 81 is 162. 162 minus 1 is 161. So we're not going to plot this point, but the y-intercept is 0, 161. Now the x-intercept takes a little bit more work, so I'm going to do the work over here. But for any function, the x-intercept is setting f of x equal to 0. So for us, it's going to be 0 equals 2 times 3 to the x plus 4 minus 1. Now, when we first were graphing, I didn't have you find the x-intercepts for these exponential functions very often. But now that we know these skills, this is a pretty straightforward log equation to solve. We're going to leave our answers in terms of logs. So isolate the exponential part first. So add 1, divide by 2. And then you can log base 3 both sides. You can natural log both sides. I usually natural log. But it's fine with me if you log base 3 both sides for this one. If you natural log, you'll pull the exponents out in front. And because there's only an x on this side, there's no x over here, I don't need to distribute the natural log 3 through. I can just divide it to the other side. And then subtract 4. So natural log of 1/2 over a natural log of 3, all that minus 4 is equal to x. I left my answer like this. Remember, this is change of base for, if you logged base 3 both sides, you could say log base 3 of 1/2 minus 4. It's much nicer to look at, so either one would be totally fine. If we were to type this into our calculator, we should see that it kind of matches up. Hopefully it's like let's see, 1, 2, 3, 4, 5. It might be somewhere around -5, according to what my graph looks like. Okay, number 2, this is a log equation, so make sure you can go back and forth. The parent function that we're looking at is y equals log base 2 of x. So the nice points on the log graph are 1, 0, and 2, 1, base number 1. And then it has a vertical asymptote of x equals 0. All right, so what's happening to this one? Now on this one, we have one of those little special cases happening. So there's a negative out in front. We need to factor the negative out from the x, from the 4 minus x, so this becomes x minus 4. So the negative is still inside of the logarithm, and we also have a negative on the outside, but now we're showing that we're going to the right 4 units and up 3. So I'm going to apply negative x because of the negative on the inside and negative y because of the negative on the outside. So that makes my points -1, 0, and -2, -1. X equals 0 would still be that. And then we're going to go, like I said, right 4, because this is actually a -4, and up 3. So the vertical line that was at x equals 0 is shifted to the right 4 units. Shifting it up 3 doesn't really do anything. And then the point that would have been at -1, 0 is going to go right 4 and up 3 there. And the point that would be at -2, -1 is going right 1, 2, 3, 4 and up 1, 2, 3. So when I sketch this in, the 2 points I have are pretty close to each other, so I don't want to get too crazy on my sketch of my graph. I'll just extend it that far. And then the asymptote equation is x equals 4. The domain for this one, because it's opening to the left, is -infinity to +4. Excuse me. You can also use inequality notation. X is less than 4 is fine. For the range, all real numbers. X-intercept. I guess it doesn't matter what order we go in. I know I reversed the order before, but let's just do the x-intercept. So that's setting the equation equal to 0. Set the original equation equal to 0, because if you made a mistake in factoring out the negative, you don't want to get both the graph wrong and the x-intercept wrong. You can get the x and y-intercept correct, even if you made a mistake in graphing, if you just correctly solve algebraically. How do I solve this log equation? I isolate the log, so I add it so that it's positive to the right side. The log base 2 of 4 minus x equals 3, so we base 2 both sides, which makes this 4 minus x equals 2 to the third, which is 8. I'm going to add x over here. I'm going to subtract 8 over there. 4 minus 8 is -4. So the x-intercept is -4, which I didn't graph, but that kind of seems right. That seems like that's on track to where I was. The y-intercept is when you plug in 0 for x. So going back to the equation, negative log base 2 of 4 minus 0 plus 3. Negative log base 2 of 4 plus 3. This is a number. We can evaluate that. The log base 2 of 4 is 2. 2 squared is 4. So this is -2 plus 3, and that's equal to 1. And I can check my graph. That seems reasonable too, the way I sketched it, so that's good. Now, if you do the algebra and you realize it's not falling in line with your graph, that might be a good time to check the graph and make sure, double check to see if you made any mistakes there. All right, parent function for this one is the log base 6 of x. So the nice points originally are 1, 0 and 6, 1. And it's got a vertical asymptote, x equals 0. The 4 on the outside affects the y. The 2 on the inside affects the x. You divide by 2. and then we'll go down 1. So 1, 0 becomes 1/2 0. 6, 1 becomes 3, 4. X equals 0 stays x equals 0, and then we're going to shift all those down 1. So x equals 0 shifted down 1 is still x equals 0. The point that's at 1/2 0 gets shifted down 1. And the point that's at 3, 4 gets shifted down 1. And I sketched this graph. This one's been stretched vertically, and we went through a horizontal shrink, dilation by a factor of 1/2. All right, the asymptote equation is x equals 0. The domain is 0 to infinity. The range is all reals. Domain, by the way, you can kind of double check your graph. Remember, you can get domain by saying 2x should be greater than 0 and solving that, so those things should coincide. X-intercept is setting the equation equal to 0. Isolate the log, add 1, divide by 4. Because this is log base 6, we can base 6 both sides. Bring this up here. 6 to the 1/4 is 4 through to 6. I don't care how you write it. Divide by 2. Make sure that you're not, you can't divide the 6 by 2 because the 2 is not underneath the 4th root. So either 6 to the 1/4 over 2 or 4 through to 6 over 2, but don't change that to a 3. And then the y-intercept is plugging in 0 for x. So 4 times log base 6 of 2 times 0 minus 1. This is no solution. We can also see on our graph there's a vertical asymptote. So even if you didn't show me the math here, there's a vertical asymptote on the y-axis, so there can't be a y-intercept for this one. All right, that finishes up graphing. The next section says evaluate and simplify each expression. All right, so we have some rules to remember. Evaluating our logs, natural log of e to the 4th is 4. Natural log of 1 over e to the 5th is -5, so minus -5. And natural log of 1 is 0. 4 minus -5 is 9. Make sure that you condense first on number 5 because our property is e to the natural log of whatever, like one single natural log equals the box, so you have to condense first. I can condense these two logarithms by multiplying their results, so this is really e to the natural log of 12, and then e to the natural log, those are inverse operations, so they cancel out, and you're left with 12. If I see parentheses with logs, we should be thinking change of base, but also because this is not a nice answer. 5 to what power is 9? 9 to what power is 29? So change of base means that we should be making this, you can either do ln or log, it doesn't matter. I'm going to do log. We should make it log of 9 over log of 5 times log of 25 over log of 9. The log 9s cancel. So now it's log of 25 over log of 5. You can't cancel out logs. You can't reduce 25 over 5 because these are inside logarithms. But you can do change of base in reverse, meaning if I've given the fraction, go backwards. This is the log base 5 of 25, and that's something we can evaluate. The answer is 2. Speaking of reverse change of base, that's number 7. So I just used logs for all of this, but change of base is also true for natural logs. So anytime you see me giving you logs or natural logs that are being divided, you should be doing reverse change of base, which means this is the log. The base number is what's in the bottom of the result, which is what's in the top. So 49 to what power is 7? 49 to the 1/2 is 7. Right? Log base 2 of the square root of 32 to the 4th. So first of all, do not figure out what big number 32 to the 4th is. instead break this down. You want your result number to match your base. So start with 32. 32 is 2 to the 5th. Oops. I said it. I didn't write it down. 32 is 2 to the 5th. That's being raised to the 4th power, and then you're taking the square root of that. Well, power to a power is, the rule is multiply. So now we have 2 to the 20th underneath the square root. And a square root is a power to the 1/2. So now it's log base 2 of 2 to the 10th. And now I can see what exponent is on that base. So the answer is 10. So I did that without ever figuring out what 32 to the 4th actually is equal to. All right, next one. I always check, can I just evaluate these logs? That answer is no. 5 to a nice power is not 100. 5 to the what is 4. But I can condense the log base 5 of 100 divided by 4, which is the log base 5 of 25, which again is 2. 5 to the 2nd power is 25. Okay, number 10. Natural log of e is 1, because remember that's e to the 1st, so that's 1. Natural log of 1 is 0, minus the log of 1 is also 0. So this is 1. I hear a lot of people asking when we're doing these, like, wait, natural log of e versus natural log of 1, which is which? Remember, it's always what power is e being raised to when you're looking at that result. So log of 1, natural log of 1, that answer is always 0. For number 11, remember when the base is 10, which it is, these are common logs, the base is not showing, so it's base 10. All you have to do is count the zeros to figure out what power of 10 that is. There are 9 zeros here, so this is 10 to the 9th, and this is 10 to the 4th. So the log of 10 to the 9th is 9. The log of 10 to the 4th is 4. 9 plus 4 is 13. So again, you should not be multiplying those actual numbers together, just thinking about their exponents. All right, and then for 12, there are a lot of ways to think about, sorry, this is bothering me. There are a lot of ways to think about, here we go, got to alternate, e to the natural log of e to the 5th. You could simplify the exponent first. What is natural log of e to the 5th? That's equal to 5. So then this becomes e to the 5th, and that's just your answer. Or you could say e to the natural log of e to the 5th. The e to the natural log cancels, and I get e to the 5th. So it doesn't matter how you think of this. There are a couple of ways to sort of approach it. But yeah, e to the 5th is as far as that would go. Okay, true or false? This is a test of like your properties knowledge. We basically have 3 properties. We have change of base, we have expanding to multiplication, expanding to division, and our power rule. And so you're just kind of checking, is this legal or not legal, basically. Natural log of x minus natural log of y, is that equal to natural log of x divided by natural log of y? That's false. I'm going to say the right side is the problem. The right side would be a change of base formula, but what it should be is ln of x minus ln of y. If you're going to condense that, it would be ln of x divided by y. So you're not dividing the logarithms, you're dividing the results within one logarithm. Natural log of x times y, does that expand into natural log of y plus natural log of x? I did switch the order there, but this is the commutative property, so you're allowed to do that. Technically, we would probably write natural log x plus natural log y, but that's the same thing. So this one's true. They expanded that correctly. Next one, the log base a of x plus the log base a of y. So those would condense into multiplication, which we have. This whole divided by 4, does that mean 4th root? Yes, it does, because remember, dividing by 4 is the same as having a 1/4 out in front, and it would be out in front of both of those, um, in front of both of those logs. So they would both, their results would both be underneath the fourth root. So that one's true. All right, for number 16, natural log of x plus y, can you expand that out? Or some people think of it as like, can I distribute a natural log through? Nope, you can't do that. There's no way to expand natural log of x plus y. It's got to be x times y or x divided by y. But also this side, natural log of x plus natural log of y. If I said condense that, hopefully you would make it natural log of xy. That's what it should be. 17 is a common mistake. This one's false. Why is that? They did the condensing on the inside correctly. Natural log x plus natural log z puts that up there, so that's fine. Minus natural log y puts the y down there, that's fine. The 1/2 does mean square root, but it doesn't put the square root on the outside of the natural logarithm. It should be on the inside. So it should be a natural log of the square root of xz over y. That's what would have been correct. Number 18, if log base a of x equals log base b of y, then x equals y. This is getting at that one-to-one property. There's only one flaw. The only time this is true is if they're the same base. And now I'm wishing I would have put another one on that was like, also false would be log base a of x equals 2 log base a of y, then x equals y. That would not be true. It's got to be just plain log equals plain log, and they have to be the same base. All right, for the next one, log base a of a over b equals 1 minus log base a of b. This one is true. Where did the 1 come from? Well, start by expanding. And I know to do that because I see subtraction here, so expanded that. Log base a of a is 1. A to what power is a? So that's where the 1 came from. All right. Next one. This is kind of almost the same thing as 13. This subtraction piece, or like kind of similar to 16. Natural log of x minus y. We can't do anything with that. So there's nothing to do there. And this is change of base if it's anything. The only thing I could change the right side into is like log base y of x, which is not that. So this one's false. This one's just not really anything. Okay. Some of you had trouble with this section when we had our first quiz. So rewrite each expression in terms of a, b, and c, where a is natural log 3, b is natural log 4, c is natural log 5. Remember, I made a list when we did these for the quiz too. The first thing you should do is expand. The second thing you should do is rewrite numbers if they're not already 3s, 4s, and 5s. Once you do that, because you might have like 3 times 4 or something, you need to expand again. And you might also simplify. Like you might have some numbers. And then the fourth step is to sub in the letters. Or maybe you simplify in that step. Okay, so let's start with 21. So I'm going to expand this first. Natural log of 15 minus natural log of 16. 15 and 16 are not the numbers I want. I want 3, 4, and 5. So break down 15. 15 is 5 times 3. 16 is 4 squared, or you could say 4 times 4. So we did expand, we did rewrite, expand again because 5 times 3. So now this can be expanded out into natural log of 5 plus natural log of 3 minus, I'm going to pull the 2 out in front, 2 natural log of 4. So remember, expand means no exponents should be left over. If you wrote this as 4 times 4, it'd be minus natural log 4 minus natural log 4. So you can combine it like that. And then the fourth step is to sub in numbers. Simplify would just be if I had like natural log of e to the something, I would simplify. Okay, natural log of 5 is c. Natural log of 3 is a. Natural log of 4 is b. I'm I'm going to leave my answer in that order. You can rearrange in any order you want as long as you keep the correct positive and negative signs intact. Okay, 22. Let's expand. So this starts out as natural log of 60 minus natural log of the square root of e. 60 is what? 10 times 6 or 2 times 5 times 6. That's not really going to work though. 60 is 12 times 5, if I'm looking at those. So 60 is 12 times 5. That's also known as 3 times 4 times 5. And we could simplify this right now. Natural log of square root of e. What power is on that e? 1/2. So minus 1/2. And then we expand again. Natural log of 3 plus natural log of 4 plus natural log of 5 minus 1/2. And then we replace the letters. So a plus b plus c minus 1/2. Again, order doesn't matter. If you wrote your letters in a different order, that's fine. Okay. Next one, expand. Natural log of 12 plus natural log of e minus natural log of 225. 12 is 3 times 4. Natural log of e is 1, so I'm going to replace that now. And 225 is 15 squared. I don't have a 15, so I could write 3 times 5 squared. I'll fix that in a minute. Let's expand. So natural log of 3 plus natural log of 4 plus 1 minus 2 times natural log of 15, which is 3 times 5. Expand a little more. This 2 should be like minus 2 natural log of 3 minus 2 natural log of 5. And then look at this. You've got natural log of 3 minus 2 natural log of 3. We might as well condense that down, or combine those like terms, I mean. So that's negative natural log of 3. So that's negative a. Natural log of 4 is plus b. I'm going to put my plus 1 at the end. So minus 2c and then plus 1. Again, the order does not matter. I would like you to combine terms. So instead of saying a minus 2a, just go ahead and fix that in the end for your final answer. And that's it. Okay. We only spent a day on those semi-log plots. And the only thing I want to take from it is if you're given a table, can you figure out whether you have an exponential function or throw back to the beginning of the beginning of the year, since we're going to be reviewing for exams soon. Do you remember how to figure out if it's linear or quadratic? So take a look at each of these. We have x and y, x and y, x and natural log y. That's a semi-log plot. And then x and y. All right, so because we're also looking for linear and quadratic, we could be doing first differences. Exponential, remember, is a common difference. So if you're looking at a table and you realize right away, like, oh yeah, this is times 3 times 3 times 3, that's great. If you're not quite sure, or if it's not as obvious to you, to find common differences, you can do like, let me write this down, common differences. Normally, if we're doing first differences, we just subtract consecutive terms. So common differences is like do 3 divided by 1, and then do 9 divided by 3, and then do 27 divided by 9, and then do 81 divided by 27. Because you have this common ratio is what I should be saying. Common ratio. Because you get the common ratio of 3 every time, this is just y equals 3 to the x. So this is an exponential relationship between x and y. If we were to graph this, it would look exponential. All right, now glancing at 25, I don't see an obvious like, times 3, but then that doesn't hold here or here. So let's check first differences. Maybe this one's linear. 2 minus negative 2 is 4. 6 minus 2 is 4. 10 minus 6 is 4. 14 minus 10 is 4. If the first differences are constant, that means that you have a linear function. This graph should look something like that. Now in the semi-log plot, remember we're looking for the semi-log plot to be linear too. If you have an exponential, if x and y are exponential, the semi-log plot is going to look linear. All right, so 8 minus 3 is 5, 13 minus 8 is 5, 18 minus 13 is 5, 23 minus 8 is 5. So because the semi-log is linear, that means that the graph of y is exponential, right? If we were to like base E all of these, we would get some sort of exponential relationship. Okay, last one is back to x and y. Is it linear? This would be minus 1, minus 3. Nope. If it's not linear and there's not an obvious common ratio, the third option was quadratic. Remember, quadratic was that you have to find the first differences, and then you also have to find the second differences. Okay, so 14 minus 15 is negative 1. 11 minus 14 is negative 3. 6 minus 11 is negative 5. Negative 1 minus 6 is negative 7. So not linear. But find these differences. Negative 3 minus negative 1 is negative 2. Negative 5 minus negative 3 is negative 2. Negative 7 minus negative 5 is negative 2. So because that's constant, it means that we have a quadratic relationship between x and y. And remember, with other polynomials, it was like if the third differences are constant, then it's degree 3, et cetera, et cetera. Okay, and then our most recent topic has been solving equations. So solve each equation for x. If the problem can be solved without logarithms, then give the answer in simplest form. That means if you can match the bases, you have to do it that way. If you give me an answer with natural logs, it might be equivalent, but it's not in its simplest form, so you won't get most of the credit. And similarly, if it's base 10 and you natural log, or if it's base E and you log, that's not simplest form either. Okay, first one, let's isolate the exponential term. So subtract 2 and divide by 3. That's going to make this 13 over 3. Common log both sides to get rid of the base 10 rather than natural logging. The common log is the inverse operation to the base 10. So 2x minus 3 equals the log of 13 over 3. And then isolate x. So add 3, divide the whole thing by 2. So log of 13 over 3 plus 3, divide the whole thing by 2. Make sure it's obvious that you're not just dividing the 3 by 2 or just dividing the log by 2. I've got to see it look like that. Okay, for the next one, I guess there are probably two ways you could start. I like to multiply the e out of the denominator to begin with, and then divide the number over here, divide by 20. But you might have also said, wait, couldn't I just do like 5e to the negative 2x equals 20, and then e to the negative 2x equals 4? We'll get to the same answer if we do that, right? So we're going to get equivalent answers if you did that. I'm just going to go with this route. I'm going to natural log both sides. Natural log of 1/4 equals natural log of e to the 2x. Natural log cancels out the base e. So if 2x equals this natural log, I get natural log of 1/4 divided by 2. So that's one answer. The alternative answer, if you did it this way, if you keep going this way, you get negative 2x equals natural log of 4. X equals natural log of 4 over negative 2. It's the same thing, right? Because the negative could be applied as an exponent. So ln of 1/4 is negative ln 4. So I would take either answer. It doesn't matter. Number 30 is one where you can get the bases to match. So 1 over 81. I like to get rid of the fractions. That's 3 to the negative 4th. and then you're still raising that to the 3 minus x. 27 is 3 to the third, which is getting raised to the 1/2 x plus 2. Because the bases match, you can drop the bases and set the exponents equal. So make sure you distribute. Negative 12 plus 4x equals 3/2 x plus 6. I'm going to get rid of that denominator by multiplying both sides by 2. Just make sure when you do that that you distribute 2 all the way through. I'm going to subtract 3x, add 24 to 12, and I get 36 over 5. All of these have been exponential equations, by the way, so I haven't had to check my answers. You only get extraneous solutions for the log equations, which are the next two. All right, I see 2 logs and a third number off to the side, so we need to condense as our first step. This is the log base 4 of x times x plus 3 equals 1. To get rid of the log base 4, we base 4 both sides. So x squared plus 3x equals 4 to the first, or just 4. This is quadratic, so get it equal to 0 by subtracting 4, factor, solve. X equals negative 4 or 1. Remember, though, you can't have a negative inside of a logarithm. So negative 4 is out because the log base 4 of negative 4 doesn't exist. It also messes up the other logarithm, but it doesn't matter. 1 is okay. Log base 4 of 1 is fine. Log base 4 of 1 plus 3 is fine. So x equals 1 is the only solution. All right, for the next one, we have logs all over the place. So, oh, and I think I've switched this. Yeah, those should be pluses on your paper. So we're going to start by condensing. This is the natural log of x over x plus 1 equals the natural log of x plus 1 over x squared plus 2x plus 1. This is the one-to-one property, or you could say base e both sides, whatever, but you can get rid of the natural logs. So x over x plus 1. Now notice here, you can factor and reduce a little bit, which is going to make the problem a lot easier. If you just cross multiply these, you're going to get like x cubed in the equation somehow, and it might be hard to solve. But I can reduce a set of x plus 1. So it's really x over x plus 1 equals 1 over x plus 1. And maybe looking at this, you can solve this right now and say, oh, x equals 1, right? But if not, if you don't catch that, cross multiply. X squared plus x equals x plus 1. That was that times that times that. X squared minus 1 equals 0. X equals plus or minus 1. But be careful with this. Plus or minus, so you get x equals 1 or you get plus or minus 1, but check both of these answers. If you check these back into the original equation, let's start with 1. Natural log of 1 is fine, minus natural log of 2. Okay, and then we just want to double check here. And then on the other side, we get natural log of 2 minus natural log of 1 plus 2 plus 1. Oh, my pen just died. So 1 works. Negative 1 isn't going to work because you're going to get natural log of negative 1. So negative 1, right off the bat, natural log of negative 1 is no solution. So x equals 1 is the only solution here. All right, for 33, you can either log or natural log both sides. I don't suggest doing log base 6 or log base 3. It gets really messy there. So I'm going to natural log both sides. Pull the exponents out in front with parentheses because they're binomials. Distribute the natural logs through. Get your x's on one side. It doesn't matter which one. Get the non-x's on the other side. Right? And then I'm going to factor an x out. Be careful with that. This should be 3 natural log 6 minus 4 natural log 3. And my last step is to divide by the parentheses. So I ran out of room, but my answer is natural log 3 plus 4 natural log 6 over 3 natural log 6 minus 4 natural log 3. Let's see if we can get these last two in before bell rings. Factor. Most of you seem to be okay when the number is e to the x here. Factors of 10 are 5 and 2. This gives me 4 e to the x, 5 e to the x, and change that to minus on your paper. Both of those are minus. E to the x equals 5 over 2. E to the x equals 2. Both of those are fine. We only throw out e to the x equals negatives. Solve by natural logging both sides. And those are my two answers there. Now, when I change the e to the x to a number, that kind of messes with some of you. So if it helps, pretend it's e to the x to begin with. So, but otherwise, this is the same exact thing. So break 3 to the 2x into 3 to the x, 3 to the x. We need the numbers that multiply to 15 that add or subtract to negative 2. That's going to be minus 5 and plus 3. Now, this is what gets confusing. You don't have to show this, by the way, but how does this work? It's 3 times 3 to the x, and it's minus 5 times 3 to the x. Minus 5 and plus 3 are negative 2, right? Then you get 3 to the x equals 5, and 3 to the x equals negative 3. 3 to the x can't equal negative 3. I can log or natural log or log base 3. Let's do that. I can log base 3 both sides. And that gives me x equals log base 3 of 5. If you natural logged both sides, change a base formula says that's the same as natural log 5 over natural log 3. It does not matter to me whether you log base 3 or natural log and get this. All right, I'm going to stop there for this video. The second video will cover the calculator problems.